Hello, and welcome to CruX UCLA, a student-led organization that aims to introduce students to the fascinating field of neurotechnology and give them the skills to develop their own brain-computer interface or BCI systems.
For our first BCI and submission to the 2019 NeuroTechX Student Clubs Competition, we used the 2016 Muse headset, the Tesla Muse Android app provided along with the Muse SDK, Google Firebase, and an Arduino microcontroller with a Wi-Fi module to turn an LED light on and off in response to the alpha power of the participant. Since the Tesla Muse Android app inherently did band power calculations for us, we wanted to delve deeper into the signal processing behind EEG signals for this year's project and explore multiple brainwave frequencies.
Our research team explored literature behind EEG dynamics and emotional states. Since the distribution of EEG powers can change based on age and gender, we knew that our BCI system would need to develop a baseline for each participant so that changes in EEG signals can be properly compared. We also became interested in articles that explored the asymmetry of cortical activity. It's commonly known that oscillations in the 8 to 12 Hz frequencies are alpha waves, which are associated with a calm or resting state of being. Beta waves are in the 12.5 to 30 Hz range and are associated with an alert and active brain, although this alertness cannot necessarily be specified to a specific emotion like anxiety. In general, right frontal lobe activity is associated with negative feelings and more rigid thinking, while frontal lobe activity is associated with positive feelings and flexible thinking. People with depression tend to have higher right frontal lobe activity than left. In other words, people tend to have less calming alpha wave activity on the right side of their brain.
This dive into the literature made us interested in extracting alpha and beta powers from raw EEG data and calculating alpha asymmetry values. We wanted to develop a BCI system that would be able to visualize this information so that people using it can understand how their brains respond to different tasks. We plan to use our Muse headset to collect and stream EEG data for this project. Although the Muse headset is consumer friendly for learning how to meditate, we had difficulty utilizing it due to the company stopping support for its SDK and several Muse related apps, such as the Test Lib Muse Android app being taken off app stores. Although Muse EEG data can be streamed via OSC, many Muse friendly OSC receivers, such as Muse Lab, were no longer available for use.
Our software team planned to develop their own OSC receiver for Muse, but due to COVID-19 and the subsequent closing of universities, many of our members and BCI equipment were relocated not just across the United States, but across the world. In November, as we reassembled with a fully virtual team, we had to make some modifications to our plan. In order to have multiple people work on the project more easily, we decided to use an EEG dataset as our input for our BCI rather than streaming the data. Specifically, we used a 2-minute long recording from the Muse headset. During the first minute of the recording, the participant closed their eyes and relaxed, and we used this data as our baseline. During the second minute, the participant counted backwards from 2064 by sevens in their head. The participant did not speak out loud in order to prevent unnecessary jaw movement that would affect the EEG data.
Our signal processing team explored several methods to analyze this data using Python. To establish the baseline alpha and beta powers over the first minute of data, we used Welch's method. Rather than run a full fast Fourier transform over the data, we chose to use Welch's method, which partitions the data into overlapping segments. A periodogram is computed for each segment, tapered and averaged to reduce variance and smooth over any non-systematic noise that may come from the signal. Welch's method is also more sensitive to non-stationarities than the FFT, which is important since the EEG data from the brain is constantly changing. Once we found our relative baseline alpha and beta powers, we compared the alpha and beta powers of the following data to it. For the asymmetry values, we decided to look at alpha waves only. We took the natural log difference between alpha powers between the left and right electrodes on the Muse headset and positions AF7 and AF8 on the 10-20 electrode placement system. A negative value would indicate greater alpha wave activity on the right side of the brain. This would mean that the left side of the brain is more active.
So what we have here is a diagram showcasing our entire system and the relationship between all of our different components in our BCI. So we've already talked about gathering EEG data from a subject's brain using the Muse headset, and then taking that data and then feeding it into a Python script, which processes the data and then gives us the percent changes in alpha and beta powers compared to the baseline alpha and beta powers, and also the asymmetry of alpha powers in the left hemisphere versus the right hemisphere. And so one thing to note is that this script processes some pre-recorded data. It is not actually process live stream data. And that is just due to the difficulties of working online for the past few months. So instead, we chose to simulate real-time streaming by basically taking this data and feeding it into a database one at a time at a given time interval. And that time interval is basically meant to simulate what it would be like to basically take a sample of data, process it, and then send it to our application in real time. So the database that we chose to use was DynamoDB. And to interact with that, we had to make use of API Gateway, which is basically a service that allows us to quickly create REST APIs to interact with a database. And the benefit of using API Gateway is that we don't have to develop or maintain our own server to basically handle any of our requests. And another component that we had to make use of was a CORS proxy. CORS is a security policy that basically is meant to combat malicious intent from sites like communicating with each other, and it requires like proper authentication to make sure that two sites are communicating properly. But we face problems with that because our web app is hosted locally. So we made use of a proxy to basically reroute all requests so that CORS proxy and API gateway basically trust each other. So as you can see here in this diagram, what we have here is Python sending the data through the proxy. It's calling the API through the proxy. And that API actually interacts with DynamoDB. So in the case of the Python script, we send a put request, and that basically is a request to update the data in the database. And then what we have here is our React web app. What that does is it reads from our database using these two rerouters. And then in our case, it outputs two graphs. And this output could basically be anything. It could be like calming music, some sort of notification, etc. And what basically any of those stimuli get fed into the subject's brain, and it creates a sort of a feedback loop. So if we switch over to our demo, as you can see, it's hosted locally. What we have here are two graphs. So this is the percent change in power, and then here is the alpha asymmetry. As you can see right now, it is not running, but if we start the proxy and then start our Python script to feed in our database, we will see that we get changes in these bars approximately every 2 seconds, and that lines up with our data streaming. And one thing to note is that the changes in bars are definitely quite large sometimes, and a way to combat this would be to sample more frequently and send our data more frequently. But for the purposes of this demo, we chose to use a window length of 2 seconds.
Although we had to adapt due to the far-reaching impacts of the COVID-19 pandemic, we developed a system that can detect and visualize changes in alpha and beta powers as well as alpha asymmetry values from raw EEG data. For the future, we aim to add detection of eye blinks or jaw clenches to our system so that they can be removed from the signal. We also aim to find and remove streamed EEG values that are too noisy due to momentary movement or loss of contact between the electrode and the participant. In addition, we could explore other signal processing methods such as wavelet transformations. In the future, we could develop a more formal feedback system based on this project. As mentioned earlier, alpha asymmetry values can be indicative of negative thinking. We could provide participants with a variety of visual feedback that corresponds to their asymmetry values to help them train their brain towards more left-sided brain activity. Testing this with many participants over multiple sessions and seeing how asymmetry values change would be a really cool experiment.
Thanks for watching.